All right, it's a snowy, well, I'm recording on a snowy Tuesday. This is lecture for Wednesday, Physics 1151. We're continuing chapter 19, which is heat, work, and the first law of thermodynamics. We're on to our third set of notes today, where we're going to cover specific heat for given processes dealing with gases and the first law of thermodynamics. Required reading, sections 19.7 and 19.8 of the text. Homework 3 will be due on the 12th, Friday, the 12th of February. And your first exam will be in lecture at 3 p.m. on Monday, the 22nd of February, and that'll cover chapters 14, 18, 19, and chapter 21. So we're going to finish chapter 19 probably Thursday or maybe Thursday or Monday. Next week we'll cover chapter 21. That's relatively short. And then you'll have about a week to get ready for the exam after that. Okay, so let's go to the notes. So, learning objectives, here's what you should be able to do when you're done with the relevant homework problems. Homework 3, reading the text and this lecture. So I use these again, as always, in your exam preparation. So before we start getting into more of the heat, work as in first law of thermodynamics as related to processes, there's a few things I want to go over again. I'm not sure I did a very good job at clarifying a few things in the last lecture. So just as a quick review, the first law of thermodynamics, recall, says that the heat added to the system plus any external work done on the system leads to a change in the thermal energy. And in this chapter, we're neglecting any changes in the macroscopic energy, the macroscopic kinetic energy and the potential energy. So say a rocket would also have macroscopic kinetic and potential energy. We're neglecting that here, and so all of the heat and the work goes into changing the thermal energy. Okay? And we have a relationship which relates the change in the thermal energy to the mass of the system, the change in the temperature, and the specific heat of the substance. And if we're dealing with moles, this mass would be replaced by little n, the number of moles. So this specific heat is a property of the material, and it's basically a measure of how much thermal inertia an object has. If it has a big specific heat, like water, it means it takes many joules of energy to change 1 kilogram by 1 degree Celsius. In other words, it's more difficult to heat it up or to cool it down. Other substances have a smaller specific heat, and a small specific heat means it takes relatively little energy to change the temperature of that substance. Next, we see from the first law of thermodynamics that both heat and work can change the thermal energy of the system. And the thermal energy depends only on temperature. So that's very important to remember here, is that the thermal energy of a system depends primarily on temperature. So for solids and liquids, in the last set of notes when we were dealing with specific heat, and we basically said that Q is equal to mc delta T. In other words, we didn't consider this external work. We were primarily dealing with solids and liquids. And in this case, the temperature is almost always changed by heat, and so we neglected W external. We set it to 0 because heat was the primary means by which the temperature is changed for solids or liquids, okay? So that's something I probably did not clarify very well. So with gases, it turns out that we can't neglect the external work, okay? Gases are easily compressed and they expand, and therefore the external work does play a large role in changing the temperature of something. And as an example, like remember recall that if we compress a gas, the gas temperature tends to increase in most processes. So whereas for liquids and solids we could neglect W external and just set Q is mc delta T, with gases we can't do that. So what we're going to see next, in addition, is that gases are somewhat complicated in that the amount of heat required to produce a given temperature change is different for different processes. And so therefore, since the amount of heat is related to delta T by this heat capacity, what that means is that this heat capacity is different for different processes. And we'll see for a minute that it differs for processes where we keep the pressure constant than for processes during which we keep the volume constant. So I think the easiest way to illustrate this is a simple example. So we've got two processes here, and in both processes we start off in the same state I. And so for both processes A and B, we start with the same temperature because they're on the same isotherm. We start with the same pressure, and we start with the same volume. Okay? And for both processes, we end at the same temperature, the final temperature, and it's the same because they're both on a different isotherm. So it's a higher temperature because we're going up. And so, but the temperature, the pressure and the volume differ at the endpoints. And also the way in which we take to go from state I to state F is different. And so the question is the amount of heat added to the system the same for both process A and for process B? Okay. So let's look at this more carefully. Both processes start at the same temperature, and they both end at the same temperature. So delta T is the same for both processes. T final minus T initial is the same for process A as it is for process B. So if delta T is the same, and the thermal energy depends only on temperature, that means that they both have the same change in the thermal energy for both processes. Okay, so what does that imply for heat? Well, it's a little easier to see if we write down our first law of thermodynamics. So we write down that the change in the thermal energy is the heat added to the system plus the work done externally on the system. Again, your author just calls this W. What he means is W external. And this change in thermal energy is equal to the number of moles, or the mass, depending whether we're dealing in terms of moles or mass, times the heat capacity, specific heat I mean, times the change in the temperature. And that change in temperature is 0 for both processes. So it looks like, since they have to add up, Q plus W external have to add up to be 0, because they have to add up to be the same delta T for the both processes, that we need to look at how W external compares to determine how Q compares. So for process A, we go from state I, the initial, to state F at constant volume. In other words, the volume is fixed here as we go along this process. And if the volume is fixed, then delta V is 0, and no work is done on the gas. W external is 0. So this, for example, could be for a gas that's in a rigid container. So W external is 0, And in this case, for process A, delta E thermal is equal to Q is equal to, this should be the number of moles. Well, I should be consistent here. It should be little n and big C, or big N and little c. But the gist of it is that Q, all of the heat goes into changing the temperature. There's no work done on it. Now let's compare that to process B. Process B, the gas is expanding because the final volume is greater than the initial. Okay? So if the gas is expanding, then delta V is positive, which means the external work done on the gas is negative. The gas is expanding, negative external work is done. So let's look here. If W external is a negative value, then that means that we need to apply more heat to get the same delta T, right? Because you have a negative number here now, which means we need an even bigger positive number, Q, to get the same right-hand side, or in other words, to produce the same temperature change. And so what this means is that for a process at constant temperature, or constant pressure, we need to supply more heat to the gas to counteract the work that's being done by the gas in expanding and give the same change in temperature. Or in other words, the heat capacity is greater for a process at constant pressure than it is at constant temperature, or at constant volume, I'm sorry. So the heat capacity does depend on the process. So just a quick summary here based on the example. If you perform a process at constant pressure, okay, suppose like for example the container is open to atmospheric pressure, you have to supply more heat to the gas to produce the same temperature change than you do for, say, a constant volume process where it's a closed container. Or in other words, the heat capacity is larger, the specific heat, for a process at constant pressure than it is for a process at constant volume. So what that means here, if we go back to our definition which relates heat capacity to heat added, is that we have to put a subscript next to these heat capacities because specific heat, is that these numbers vary depending on if the process is done at constant volume or whether it's done at constant pressure. And so we're going to put a V for the heat capacity at constant volume, and we're going to put a P, subscript P, for the process, for the specific heat at constant pressure. And we saw in our example before that the specific heat at constant pressure is greater than the specific heat at constant volume. Now we're primarily going to be dealing with ideal gases, and I remember ideal gas is just a gas that the density is not so high that so the interactions between the molecules can be neglected. They're basically, you can think of them as just balls bouncing back and forth along the wall, hitting the walls of the container. So for ideal gases, it turns out that the heat capacity at constant pressure is larger than that at constant volume by the same amount for all gases. And this R, remember, is the ideal gas constant. That's from PV is equal to nRT. And so the difference between these heat capacities is the same for all ideal gases. It's equal to R. And here's an example for a monatomic gas like helium, single atom. The heat capacity at constant volume is 3/2 R. The heat capacity at constant pressure is 5/2 R, and the difference is 5/2 R minus 3/2 R is R. For a diatomic gas, oxygen, nitrogen, with two molecules, two atoms, CV is 5/2 R, CP is 7/2 R, and again the difference between the two is R. And so the heat capacity at constant specific heat is always larger for constant pressure than at constant volume. Now, for processes other than constant pressure, which is isobaric, or constant volume, which is isochoric, the relationship between Q and delta T is more complicated, and we need to use the first law of thermodynamics to relate them. Okay, so what we're going to do next is we're going to look a little more closely at how the heat added is related to temperature changes for each of the four processes: isothermal, isochoric, isobaric, and adiabatic. And we discussed the middle two a little bit, isochoric and isobaric. So what we do here, if we can rearrange the first law of thermodynamics, we can put Q alone on the left-hand side, and what we see is that the heat added is equal to delta E thermal minus the external work. So let's look at this for each of these four processes. And again, on the exam, it's important to understand each of these processes, what's going on, how the temperature, pressure, and volume are related for each process, ideal gas law, and how to apply the first law of thermodynamics for each of these types of processes, including how the PV diagrams look for them. So let's look at each of these individually. So recall that isothermal process, constant temperature, delta T is equal to 0. And so in this case, there is no change in the thermal energy of the gas or the system in general. So in this case, if delta E thermal is 0, then Q is equal to negative W external. And so all of the heat added, if Q is positive, then W external is negative, meaning a gas expands. And so in other words, if we keep the temperature of the gas constant and we apply heat to the gas will expand. Okay, so all of the heat entering the system is used by the system to do work. In other words, it does work against the external pressure, and the gas expands. Okay, so if the temperature doesn't change and we apply heat to a gas, the gas will expand. If we remove heat from the gas at constant temperature, the gas will compress. Okay, and so that's an isothermal process. So you should be able to know that an isothermal process implies delta T is 0, so delta E thermal is 0, and then Q is equal to the negative external work. And you should be able to explain in words what's going on here in this isothermal process. Okay, the second process again is isochoric, and isochoric means the delta V is 0. And so again, we use our example for a gas. This would be if you have a rigid container that can't expand or contract, and to some extent, your car tire approximates this. So what happens here, if delta V is 0, if the volume doesn't change, then no work is done on the system or by the system. So W external is 0 if no volume change. And in that case, Q is delta E thermal. And then we can write the change in thermal energy in terms of the change in the temperature. Okay? So in other words, if the gas cannot expand or contract, meaning you have a rigid container and it's confined, then all of the heat that goes into the gas is used to change the gas's temperature. None of it is used to do work. It's all used to heat it up. And similarly, if heat is removed from the system, from the gas, then the temperature will decrease. Okay. So in this case, if the volume can't change and no work can be done, all of the heat added or removed goes into changing the temperature. And that's different from the isothermal, where if we keep the temperature constant, all of the heat added or removed from a system goes into work. Okay. So again, you should be able to apply the first law of thermodynamics to an isochoric process and explain what's happening, in addition to providing an example of a practical system that approximates this. Okay. Now we go to isobaric, and remember the pressure is constant, and so the integral of the external work, since P is a constant, you can pull it out of the integrand, and we get that the external work is negative P times delta V. So if delta V increases, meaning the gas expands, external work is negative. If delta V is negative, meaning the gas contracts, the work done externally is positive. Okay? And so in this case, we can write the first law of thermodynamics isn't as simple because none of the three terms are zero, but we can still nevertheless write it as the heat added. Some of the heat added goes into changing the temperature. Some of the heat added goes into changing the volume. Okay? And this is why, because this term here, the work is not zero, this is why you have to supply more heat to change the temperature, because some of this heat is going to go into expanding the gas and not just changing the temperature alone. So we need to apply more heat, supply more heat to get the same temperature change. And this is a gas and an open to the atmosphere. So you should be able to understand now why the heat capacity is greater at constant pressure, why you need more heat to change the temperature than if you do at constant volume, where none of that heat is going to go into expanding the gas. See here, all the heat goes into changing the temperature, so we don't need to supply as much heat. So the last process is particularly interesting, and this is an adiabatic process. We touched on this briefly. And for adiabatic, remember, this is for an insulated system, okay, where Q is equal to 0. No heat is added, no heat is lost. And an example of this, remember, was your calorimeter, where you had the water inside the beaker and then you put styrofoam around it so that no heat could enter or leave. And in this case, for an adiabatic, Q is 0, so the first law of thermodynamics says that W external is equal to the change in the thermal energy, and that's related to the change in the temperature. And for adiabatic, since no heat can come in or leave the system, all of the work done on the gas goes into changing its temperature. And each of these we're going to see later when we deal with a four-stroke engine. In each of the processes of the internal combustion engine is associated with one of these four types of each of the four stages is equal to each of the four stages corresponds to one of these processes. And so if we compress a gas without heating it, so this is called an adiabatic compression. Compression means delta external is positive, and that means the temperature will increase. Delta T is positive. So if we insulate the gas and we compress it, if no heat can be added or leave, the work done on the gas goes into heating it up. So compressing a gas heats it up. Conversely, if the gas expands and no heat can enter or leave, W external is a negative number, which means delta T is negative and the gas cools. So an expanding gas with no heat added or removed from the system, the temperature will decrease. and a gas which is compressed adiabatically will heat up. So there's two practical cases of these processes that are pretty close to adiabatic in nature. We've already talked about the first one. If the container is insulated, so either the calorimeter, in which case you have styrofoam surrounding the container, or also if you have a piston of an internal combustion engine, when we close the intake and the exhaust valve so that air cannot enter or leave, this is approximately adiabatic. A second type, which isn't so obvious, is many processes can be done so fast and the state changes so rapidly that it does not allow time for the heat to enter or leave the system. And so, in other words, Q is 0 if the process is done very rapidly so that the system doesn't have time to gain or lose heat. And here's an example which is very dear to us, especially if you live on the western side of Watauga County. It's called adiabatic expansion and compression due to air over a mountain. Okay, so here you have air, and here you have the west side of the mountain. And if any of you ever went hiking in Colorado, you can see it a little bit here, but it's really obvious in some parts of Colorado. If you stand on the tip of a mountain and you look over to the west, you'll see more green vegetation. And if you turn the other way and you look to the east, you'll tend to see often less vegetation. It's drier. So why is that? Okay, well, more often than not, the synoptic airflow of air goes from west to east at the mid-latitudes, okay? And so on the west side of the mountain, suppose that we have moist air like we do today, as I'll see when I shovel after class. So you have moist air coming from west to east, and it's got a lot of water vapor. It has a lot of water vapor in the air. So what's going to happen here? This air is going to rise, and it's going to rise pretty quickly. It's got to rise to go over the mountain. And if it rises rapidly, we can approximate this as an adiabatic process. It doesn't have time to exchange heat with its surroundings. So set Q equal to 0 here. So what's going to happen is the air is going to rise, and remember, as we go up in altitude, the pressure decreases, and so the pressure confining that air parcel is less, and so the air tends to expand. Remember, air expands as it rises. So as it expands, it's going to cool, and as it cools, if it has enough moisture, it can cool enough for the air to saturate, and when the air saturates, this water vapor condenses. And it condenses and it forms clouds, and it can form rain, or as in today and yesterday, snow. So what happens is as the air is coming up the west side of the mountain, when the winds are from the west, you can get this condensation if it's moist air, and you get rain on the west side of the mountain. Okay, so now here comes the air, it goes up, it comes over. Now we've already rained out some of the water, so a lot of that moisture is gone. And in addition, now the air is going to drop as it goes over the mountain. And as it drops, remember, the pressure will increase because the pressure is greater, and so that the volume will decrease, and you get this compressed air. You have a high pressure region, and if you have compressed air, then you have addition, you have less moisture in the air. Compressed air will heat, which means it won't saturate. You have compressed air, you've already rained out some coming from west to east, and that's why a lot of times on the eastern side of the mountain, you will not have rain at the same time when you're getting rain or snow on the west side. And so that's why a lot of these times the eastern slopes will have no snow or no rain, and the western side will be getting dumped on. And if you drive around the county today, you will see that there was much more snow near the Tennessee border than there was if you go a little bit east of Boone along the Blue Ridge. And so a lot of times these eastern facing slopes will be what's called a rain shadow, and you get more precipitation on the west. So this is a practical example of adiabatic expansion and compression as it relates to weather. Now that can change. Now if you have, for instance, if you have flow coming from east to west and it's coming up along the Blue Ridge, in this case the eastern side will be getting dumped on, and you'll be getting less snow on the western side. So it's just more often than not at these mid-latitudes, the prevailing wind direction is from the west to east, and so the western sides more often than not will be getting precipitation more than the eastern sides. But it can change if you have winds coming this upslope flow from the east. So this is an example, a practical example of adiabatic expansion and compression that you may know very well if you're driving through Watauga County today. Now in the adiabatic processes, the pressure and the volume change in a little bit different manner. So remember, for an ideal gas, PV is equal to nRT. Well, for an adiabatic process, your book derives the fact that it's P times V to the gamma is constant in an adiabatic process. Okay, for an isothermal process where T is constant, PV is constant. But here it's PV to the gamma power is a constant. In other words, we can write it, if I is the initial state and F is the final, we can write it as P initial, V initial to the gamma is P final, V final to the gamma, where gamma is just the ratio of the specific heats at constant pressure and at constant volume. And for a diatomic process, since Cp is 5/2 R and Cv is 3/2 R, the ratio Cp over Cv is 5/3. And for a diatomic gas, since Cp is 7/2 R and Cv is 5/2 R, the ratio is 7/5. And this is derived in the book. I don't want to spend a lot of time. The derivation isn't difficult. It involves using the first law of thermodynamics, the ideal gas law, and some algebraic manipulation. So I encourage you to look at it, but I would rather not spend time deriving it in class. So you should be able to just use this relationship. So on an exam, put this on your note card. And you can also, using the same approach, and it's derived in the text, there's a relationship for how temperature and volume change in a adiabatic process. So if we solve this, if PV to the gamma is constant, that means the pressure must be a constant times V over gamma. And gamma is always bigger than 1. It's always a number bigger than 1. And so if we compare this to an isothermal process where PV is a constant, meaning P goes as 1 over V, in this case, the pressure decreases faster with increasing volume. It's PV to the gamma, where gamma is bigger than 1. And if we draw these adiabatic curves which are constant along the basically, it's how the process evolves adiabatically. We see that pressure decreases more rapidly with volume. The slope is larger for an adiabatic process than for an isothermal process. So that again is just an example of these PV curves again, where these what's called an adiabat is how the pressure and the volume change in going from one state to another if we don't add or remove heat. We basically ride the curve here. Whereas the isothermal curves are how pressure and volume change if we hold the temperature constant, we ride this curve. That's called an isotherm. So in other words, the pressure decreases more rapidly with increasing volume if we don't add or remove heat than for an isothermal where the temperature's constant. Okay, so let's finish the lecture with an example here. And we're back to our PV curves, PV diagrams here. And we have two processes, process A and process B. And in both processes, we start at the same temperature, Ti, and we end at the same temperature. And in both processes, we start at the same volume and the same pressure, because it's the same point on the PV diagram. And in both processes, we end at the same pressure and the same volume. So in both processes, going from route A to route B and getting from initial state to final state, we start and end at the same temperature, the same pressure, and the same volume. So we might think, oh, well, the heat added to the system or removed must be the same for both. Okay, well, let's see. So in order to examine this, we need to go back to here's our first law of thermodynamics again. Again, put this on your note card for the exam, which says that delta E thermal, the change in the thermal energy, is always equal to the heat added plus the external work done on the gas. Okay? So we use this and the fact that E thermal depends on temperature. Okay, well, both processes start at the same temperature. Both processes end at the same temperature. So for both process A and process B, delta T is the same. And if delta T is the same for both, then delta E thermal must be the same for both processes. Okay? So that still doesn't help us to determine which one the heat added or removed is greater. So what we need to also do, so delta E thermal is the same for process A and B. In order to say which one has more heat added, we need to look at which process, A or B, has a higher value of external work. Okay, so let's look at this. If we always remember that work is always equal, the external work is equal to, we find the area under the curve in going from A to B. So it's the area under the curve, and we tack on a negative sign because it's external work, right? And so here we're going to a larger volume. So we find the area under the curve, and delta V is positive because it's expanding, which means external work is negative. So we find the area under the curve for both processes, and then we tack on a negative sign because the gas is expanding. That's external work. So let's look here. The area under the curve in going from A to B is larger, or from I to F on process A is larger than the area under the curve on process B. So that means that W external must be a larger negative number for process A. There must be more negative external work done in expanding the gas by A than in B. Okay? And if it's a larger negative number for process A, then that means we need a larger positive number Q to get the same delta E thermal. Or in other words, again, we have to supply more heat if we're going from state I to state F along process A. We have to supply more heat to counteract the work done by the gas in expanding in process A. So QA has to be greater than QB. Okay? And this is another example, again, on the exam. I can't stress this enough. You are going to have to understand these PV diagrams, and you're going to have to be able to use those along with the ideal gas law and the first law of thermodynamics to relate heat and relate work for different processes. So this is another example of this. There will be more in the homework. So I think that's enough for today. There was more examples on your homework problems, and we can go over more on the Monday live lecture where we're all together. So start to work on your homework problems, read the chapter, and look at your unit learning objectives, and stop by during office hours always if you have any questions. Have a good day. Enjoy the snow. I'm off to shovel.